Hello friends, I am Aditya Bhavne. Today we are going to learn reaction water turbine, that is Francis turbine. So basically in this case there are two to three types for reaction turbines. Among that we will learn Francis turbine. So during this session we will able to understand the working of Francis turbine and will be able to solve the numericals. Now let us see classification of reaction turbine. So basically we know impulse turbine is purely kinetic turbine, or that is pellet wheel is impulse turbine, and for reaction turbine it is mixed type or kinetic and pressure energy. The energy which is involving to rotate the shaft or that rotor is consisting of kinetic energy and pressure energy. So based upon the direction of water flow in the runner, there are three classifications. First one is radial flow turbine. In case of radial, there is radial inward and radial outward. Let us say there is a one disc in which water is coming from outside towards the shaft, that is radially inward turbine. And if the water coming out from the shaft and moving towards periphery, it is called as outward flow turbine. Second classification is axial flow turbine, which is example of that is Kaplan turbine, in which water enters and leaves through the shaft in axial direction only. In which again there are two types, Kaplan and propeller. In Kaplan, there is a blades or rotor blades are movable and adjustable, while in case of propeller turbine, it is fixed. Generally, we use propeller turbine for generating the energy from sea tides. Next classification is mixed flow turbine, that is Francis turbine, which is basically we call it as radial inward turbine. Now if you see this layout, what we can see, water which has been stored inside the dam, which has been carried through the penstock or pipe, and it has kinetic energy. That kinetic energy has been given to this scroll casing. In this case, the kinetic energy has been converted into pressure energy, partial pressure energy, and that kinetic and pressure energy both are being used to rotate this shaft. And at the exit, we have draft tube. So draft tube is nothing but a pipe which will discharge the water from this turbine exit to tailless level. And whenever this shaft will rotate, the electricity will be generated. Then that electricity will transfer from here to another location, wherever we require. Now in this case, inward flow reaction turbine having radial discharge at outlet is called as Francis turbine. If you see at the exit, it is axial movement, or I can say radial discharge, and those type of discharge we can say it as Francis turbine. Whenever we heard radial discharge at outlet, which means that turbine is Francis turbine. Now in modern turbine, the water enters the runner of the turbine in radial direction at outlet and leaves in the axial direction at inlet from the runner. Now what this is saying, from outer periphery it is moving inside, outer periphery to inside, and leaves axially. Thus Francis turbine is mixed flow type of turbine. So basically we know impulse turbine or Pelton turbine is for basically high head, that is greater than 250 meter of head. But Francis turbine is mixed type of turbine which can be used for low head as well as high head. So that is ranging from 50 meter to 350 meter. So it can be used greater than 350 meter if we are optimizing the blade shapes and the velocity. Basically in USA and China, they have used up to 400 meter the Francis turbine, and they are getting higher efficiency. So let us understand the working of Francis turbine. So if you see, there are many components. Basically, water inlets from penstock. Okay, if you see this, water is entering from this penstock to turbine. So this water will enter from this case from here, and it will move from this way. So it is area is decreasing gradually. What is the purpose of area decreasing? To maintain the velocity at constant flow rate and pressure, so that velocity at each location or velocity of fluid will move or exert a pressure with same thrust. In this case, we can see this is scroll casing, which is outer protective covering. This is movable blades. We can adjust these blades through which water will enter. This is guide wheel, so that guiding mechanism. We can change this angle by rotating this guide wheel. Inside this, there is a runner blades which will rotate whenever water will impart from this section to inside. Here you can see that water enters radially inward. Okay, water enters radially inwards and leaves axially. So it enters radially and leaves axially. So what are main components of this? Spiral or scroll casing. So this is spiral or scroll casing, which is having decreasing area, cross-sectional area. Next is penstock, that is inlet pipe. Then guide vanes or wicket gates. So guide vane. Okay, then governing mechanism, that is through guide wheels. Then runner and runner blades. So inside this runner blades and this disc runner, and at the end the draft tube. So let us learn one by one in detail for components. Penstock, we know the water which is been stored in the dam, carried through the large pipe, and it is been provided to turbine inlet. So water is provided to turbine runner from the dam. We say it as penstock. Second is scroll casing. So scroll casing is nothing but outer area of the turbine. So penstock connected to the and feed waters directly into the annular channel surrounding the turbine runner. The channel is spiral in its layout. The runner is completely closed in an airtight spiral casing. The casing and runner are always full of water. So one thing I would like to notice here, in this case, there is always water present all over this system. While in case of Pelton turbine or impulse turbine, we can say that it was running under atmospheric condition. But in this case, it is closed conduit. So what it means closed, there is a variation of pressure and velocity. So I can say it is closed conduit. So pressure will be varying. It is not atmospheric pressure. At the inlet, it will be atmospheric pressure, but when it leaves, it has different pressure or lower pressure. Since the velocity and pressure energy can be absorbed by the runner. Next is guide vane. A series of aerofoil shaped vanes called the guide vane are arranged in a casing to form a number of flow passages between the casing and runner blades. So guide vanes are fixed in position. So if you see this, these guide vanes are fixed in position. We can later change its position if we want to change the load on the turbine. Next is guide wheel and governing mechanism. So what we know guide wheel, it will change the position of guide blades to affect the variation in the flow rate in the wake of changing load condition on the turbine. When the load changes, the governing mechanism rotates all the guide blades about their axis through the same angle so that the water flow rate to the runner. So again in this case, we can adjust the flow rate. Let us say in summer, water quantity decreased inside the dam. So what it means, the flow rate or velocity will decrease. So to compensate that, we can reduce the uh, angle between these two so that it will increase the velocity and the turbine speed will remain same. So we can adjust this guide blade angle through guide wheels. That is guide mechanism. So it consists of circular wheel all around the runner of the turbine. The stationary guide vanes are fixed on the guide wheel. The guide vanes allows the water to strike the vanes fixed on the runner without shock at inlet. So what are the purpose of this guide vanes? Water should enter to the runner without any shock. if we change the guide blade angle in such a way that water will strike to first guide wheel or vane, then what will happen? The energy will be absorbed by this blade. So the angles have been set in such a way that it should not strike, it will move towards this periphery of turbine runner, and it will impact that runner blade, so that there is a one type of pressure difference. One side will be higher pressure and one side will be lower pressure due to velocity impact, and which will cause the rotation of this disc or shaft. Next components are runner and runner blades. So runner of the Francis turbine is a rotor which has passages formed between the draft tube and scroll casing. It is circular while on which a series of radial curved vanes are fixed. The vanes are so shaped that the water enters and leaves the runner without shock. So these are also in such a way that shaped, so it will do not hamper or have a shock to these blades. So water enters and give its kinetic and pressure energy and leaves axial. So last component is draft tube. So draft tube is after passing through the runner, the water is discharged to the tailless through a gradually expanding tube. So we are increasing the area of this draft tube from inlet section to exit. Why we are increasing this? Because of the pressure which is being at the exit of this turbine will be negative, or in some time it will be in vacuum. So if you are discharging that low pressure water to tailrace or atmosphere, so it will create a back pressure, or as well as it will create a cavitation to this surface. So to avoid cavitation and to utilize this energy, exit velocity energy, we will be providing a draft tube which will reduce the velocity and increase the pressure nearly about the atmospheric pressure. So the pressure at the exit of the draft tube of reaction turbine is generally less than the atmospheric pressure. The water at exit cannot be directly discharged to tailrace. That is what I was saying. A tube or pipe of gradually increasing area is used for discharging the water from exit of turbine to the tailrace. This tube of increasing area is called as draft tube. So whenever the cross section increases gradually, so we can see it as draft tube. So one end of draft tube is connected to the outlet of turbine, while the other end is submerged below the water of the tailrace. So one is connected to the turbine exit and other end is connected to tailrace, which is inside the tailrace level. So there are two main terms, stay vanes and guide vanes. From this you can clearly understand how the water has been flowing from outer periphery to inside the turbine. So the basic purpose of stay vanes and guide vanes is to convert a part of pressure energy of the fluid at its entrance to the kinetic energy, and then to direct the fluid onto the runner blades at the angle appropriate to the design. So during the design we are going to set the shape of these blades so that water will enter and leave without shock. So kinetic energy is being imparted to the stay vanes. Moreover, the guide vanes are pivoted and can be turned by a suitable governing mechanism to regulate the flow while load changes. So earlier I told you that whenever the flow rate changes or load changes, the turbine require more energy to rotate the shaft at same speed. To maintain the same speed, what we require large flow rate, or in some case less flow rate according to the load. So according to the load, we can change this direction of guide vanes. So guide vanes are also called as wicket gates. The guide vanes imparts a tangential velocity and hence angular momentum to the water before entry to the runner. So what these guide vanes do? This will provide a tangential velocity to the runner blade at inlet and provides angular momentum, that is, it will provide a force so that this will rotate. The guide vanes are constructed using optimum aerofoil shape in order to optimize of design performance. Why they are used aerofoil shape? Because we need to minimize the stresses and force. Here you can see that how the water is moving from outlet to inlet section. Next topic is net head at turbine run. So in this case, if you understand this, this is the headrace level up to which water is being stored, and in this case, the tailrace level where water is discharged. Okay, so water is stored and water is discharged through draft tube. Now let us say the height which is from tailrace to headrace is called as gross head or total head. And what is net head? Net head is what? Actual head that is been required to produce the power. So HF is what? Frictional head. So that should be neglected or removed from actual head, total head. So I can say net head equal to total energy available at exit from the penstock. So total energy exit from penstock minus total energy available at exit from draft tube. Total energy available from exit of draft tube. So that is given by pressure rate plus velocity rate and potential energy. That is P by rho g plus V square by 2g plus Z of penstock minus whatever energy that has been lost in draft tube, that is P by rho g plus V square by 2g plus Z of draft tube. Let us understand if draft tube is not been submerged inside the water and which is being created at this point only. Okay, so gradually increasing area to this point. In that case, what will happen? The pressure will remain same, atmospheric pressure, and the atom we are considering from this tailrace level, so it will becomes zero. Z will become zero in this case. So if we are considering a atom at tailrace level, so in this case this will become zero, this will become zero. So the equation becomes H equal to P by rho g plus V square by 2g plus Z. The penstock minus draft tube velocity at exit by 2g. Now next, if we neglect this draft tube exit velocity, it is quite less, and we are designing in such a way that its whole kinetic energy is being utilized. In that case, net head will be E by rho g plus V square by 2g plus Z. Now let us understand the kinetic energy or diagram at input triangle and output triangle of Francis turbine. So this is inward flow. So water moving from outward periphery to inside the shaft, toward the shaft. So we know velocity at inlet, that is Vf V1, Vf1 flow velocity at inlet, alpha velocity angle made by jet, in this case inlet velocity of water. So this is Vr1 relative velocity, theta angle of this vane, bucket angle, in this case vane angle. Vr2 relative velocity at exit, Vf2 equal to V2. Since in this case discharge will always be radial, so Vw2 will be 0 and beta will be 90 degree. So Vf2 equal to V2. And here is change, U1 will not be equal to U2 as in case of Pelton wheel. So here U1 and U2 are different since the flow will input at radial direction and exit in axial direction. Let us understand what we know work done. M dot Vw1 plus Vw1 U1 plus or minus Vw2 U2. Now in this case what we know, M dot rho AB. So rho AB is nothing but rho Q. So again I can rewrite as rho G by Q multiplied by G and divided by G. So we know rho G is nothing but W. So W Q by G. So this equation will remain same. Work done equal to M dot in bracket Vw1 U1 plus or minus Vw2 U2. So if the flow is radial, we know flow is radial. So Vw2 equal to 0. So work done equal to M dot Vw1 U1. Next term is hydraulic efficiency. Hydraulic efficiency is equal to power developed by the runner divided by power supplied to the runner. So power developed by the runner is nothing but whenever this runner will rotate. So that energy is nothing but m dot Vw1 u1. And power supply to the turbine is nothing but water power, that is rho g qh. So hydraulic energy equal to, so this rho will get cancelled, rho will get cancelled. So area into velocity is nothing but q, and q, this q will get cancelled, Vw1 u1 by gh. Next is mechanical efficiency. Mechanical efficiency equal to shaft power by power developed by runner. So shaft power is PS, and power developed by runner is nothing but m dot Vw1 u1. Next is overall efficiency. Overall efficiency is output power by input power. So output power is shaft power and input power is water power, that is rho g qh. Next is working proportions of Francis turbine. So ratio of width to diameter is nothing but d1 by d1, which ranges from 0.1 to 0.45. Next is flow ratio, kf equal to vf1 by under root of 2gh. So which will be ranging from 0.15 to 0.9. Next is speed ratio, ku equal to u by under root of 2gh. So we can remember this formula by vf equal to kf into under root of 2gh and u equal to ku into under root of 2gh. So here this is change for discharge, since entry is radial and exit is axial. So discharge can be calculated as pi d1 b1 into vf1 at inlet, at equal exit pi d2 b2 vf2. Since flow rate or water quantity will remain same at inlet and outlet, so this two equation can be equated. From these two equation we can find out diameter at inlet or diameter at outlet, or width at inlet or outlet, or flow velocity at inlet and outlet. So again here number of vanes varies from 16 to 24. In order to okay, we have 10 minutes more. We'll quickly finish up. So number of vanes varies from 16 to 24. In order to avoid periodic impulse, the number of vanes should be either one or more or less than the number of guide vanes. So basically the number of vanes are kept between 16 to 24. Now in case of Pelton wheel, what we know formula, calculate the number of buckets, Z equal to 15 plus 0.5, that D by D ratio. Okay. Now in this case it is 16 to 24. So we will start numerically next session. So you will be getting everything. So at the end of this session, you will be able to answer the working of Francis turbine and its few terms: net heads, then hydraulic efficiency, Pelton, then overall efficiency, and lastly turbine. Thank you. If you have any doubts, please ask in chat box. Yeah, everyone just type your roll number in chat box. 33, 35, 56, 05, 67, 3, 26, 24, 06, 25, 30, 63, 38, 60, 54, 17,